Until now, we have explored the various modes of convergence, and we have seen how they are interrelated with each other, and we have seen the various implications and the failure of the reversal of many of these implications. And in this lecture, we will look at some limiting properties of the modes of convergence. In particular, we will ask the following question, that if Fn converges to F in some mode of convergence and the same sequence converges to some other function g in the same mode of convergence as the above one, in the same mode of convergence, then is it true that F equal to G? And in fact, we can ask a more general question. More generally, if Fn converges to F in one of the seven modes of convergence, and Fn converges to G in any other mode of convergence, then is F equal to G. So, this is about the uniqueness property of the limits, and we can, first of all, we can easily see that if we demand that F equal to G everywhere, this is not going to be true even in the case of pointwise almost everywhere convergence. So, we have to relax our expectation a little bit, lower our expectation a little bit, and we only ask that F equal to G almost everywhere. Similarly here, even if you have two different modes of convergence for Fn going to F and Fn going to G, then F equal to G almost everywhere, and the answer to both these questions is in the affirmative, and we will prove this in this lecture. So, let's begin with the following lemma. So, here is the statement of the lemma. So, we have a measure space x be mu, and we have two sequences Fn and Gn of measurable functions on x, complex measurable functions, and suppose that F and G are additional measurable functions. Then the first part says that Fn converges to F in one of the seven modes of convergence if and only if the modulus of Fn minus F converges to 0 in the same mode. So, this is the first part of the statement. The second part is that if Fn converges to F in one of the seven modes again, and Gn converges to G in the same mode as Fn, then Fn plus Gn converges to F plus G in the same mode again, as well as alpha Fn converges to alpha F in the same mode for any complex number alpha. So, the first part is actually very easy, but it's just that one has to check for each of the seven modes that this is true, but it's quite easy, and I leave it as an exercise. So, I'll only prove the second part. The second part is essentially just the use of triangle inequality in its various forms, and I will only prove it for convergence in measure. So, let's look at the proof for 2 when Fn converges to F in measure and Gn converges to G in measure. Then I want to show that Fn plus Gn converges to F plus G in measure. To show this, let epsilon be a positive number and denote by Fn epsilon the following set. This is the set of points in X such that modulus of Fn x minus Fx is greater than or equal to epsilon. Similarly, we defined Gn epsilon as the set of points in X such that Gnx minus Gx is greater than or equal to epsilon, and finally Hn epsilon is the set of points in X such that Fnx plus Gnx minus Fx plus Gx is greater than or equal to epsilon. So, since Fn converges to F in measure, this is equivalent to saying that the measures of these sets Fn epsilon goes to 0 as n goes to infinity. Similarly, we have that the measure of Gn epsilon goes to 0 as n goes to infinity, and we have to show that the measure of, so we have to show that the measure of Hn epsilon goes to 0 as n goes to infinity. So now note that if epsilon is less than or equal to modulus of Fnx minus plus Gnx minus Fx plus Gx, then by the usual triangle inequality we can write this as less than or equal to modulus of Fnx minus Fx plus Gnx minus Gx. So if x belongs to Hn epsilon, then by this inequality this implies that x belongs to either Fn epsilon by 2 or x belongs to Gn epsilon by 2, meaning that at least one of these terms is greater than or equal to epsilon by 2. So this means that Hn epsilon is a subset of Fn epsilon by 2 union Gn epsilon by 2, and so the measure of Hn epsilon is less than or equal to the sum of the measures Fn epsilon by 2 plus the measure of Gn epsilon by 2, and the right hand side goes to 0 as n goes to infinity, because both these terms go to 0. So this means that Fn plus Gn converges to F plus G in measure. Equipped with this lemma, we can state the following theorem about uniqueness of limit with equality almost everywhere, and it says that if Fn is a sequence of measurable functions and F and G are two additional measurable functions, and now suppose that Fn converges to F in one of the 7 modes of convergence and Fn also converges to the function G in the same mode or in any other mode. So for example, Fn can converge to F pointwise almost everywhere, and Fn also converges to G. It can be either pointwise almost everywhere or in any other mode like convergence in measure or L1. Then we have F equal to G mu almost everywhere. So it means that as long as you have convergence to two different functions in any of the 7 modes, then the limit of the functions will agree outside a null set. So let's see a proof of this theorem. To start the proof, it's helpful to go back to our map of implications, which will help us reduce the number of cases to consider in our proof. So here notice that no matter where you start, whether you start at uniform or L infinity or almost uniform or pointwise, you either end up, if you follow the chain of implications, then you either end up in pointwise almost everywhere convergence, either end up here, or you end up in measure convergence. So either 1 or 2. So for example, if you start with uniform, you can go to pointwise and then to pointwise almost everywhere. Similarly, you can also go this way and end up in measure convergence. If you start with L1, you end up in measure convergence, and so on. Because these arrows are not invertible in general, so we cannot go backwards. So it's either pointwise almost everywhere or convergence in measure. So this means that without loss of generality, we can assume that Fn converges to F pointwise almost everywhere, and Gn converges to G or in measure. So Fn converges to F pointwise almost everywhere or in measure, and Gn converges to G also pointwise, either pointwise almost everywhere or in measure. So this is the first reduction that we can make, because our chain of implications lead us to these two modes of convergence. Now if both this should be Fn, if both Fn converge to F and Gn, Fn converges to G in the same mode, say pointwise almost everywhere, then by our lemma, by the previous lemma, we have that Fn minus Fn. So we choose the two sequences Fn and minus Fn and we add them, so you get the 0 sequence. This converges to F minus G. So this is by our previous lemma, because if you had two sequences that converges to F and G, then their sum converges to F plus G, and so we have this. But this means that F minus G, so this is pointwise almost everywhere, but since this is a constant sequence, this means that F minus G equals to 0 almost everywhere. So this means that F equal to G almost everywhere, and we are done. Similarly, if you are considering measure convergence, one can use a similar argument to conclude that F equal to G almost everywhere. So check that the same argument holds for measure convergence. So we are only left to prove we can use the symmetry of the equality almost everywhere. So by symmetry, it suffices to show that if Fn converges to F pointwise almost everywhere and Fn converges to G in measure, then these two things imply that f equal to g almost everywhere. So by reversing the roles of g and f, you can get the reverse case where fn converges to f in measure and fn converges to g in pointwise. Then also this should hold. So to show this, it further suffices. So we have to show first that the set x in x such that mod fx minus gx is greater than 0, strictly greater than 0, is a null set, is a mu null set. So if we want to show this, it further suffices to show that given any epsilon greater than 0, the set x in x such that modulus of fx minus gx is greater than epsilon is a mu null set. Because if we write this as a0 and if we write this as b epsilon, then a0 is the union, countable union n equal to 1 to infinity b 1 by n. So we can describe this set a naught where fx minus gx is strictly positive, the modulus is strictly positive with respect to these sets b epsilon by choosing epsilon to be 1 over n and taking the union. And if each of these b 1 by n are mu null, then the union is mu null. So we have reduced it to proving that this set b epsilon is a mu null set. So let's see. To the contrary, we suppose that the measure of b epsilon is strictly positive. Then we define the following set. We define fn to be the set of points in x such that f capital N fn minus x fx, the modulus, is less than or equal to epsilon for all n greater than or equal to n. So sorry, here I should take x in a0. So these are all subsets of a0. So note that fn is a subset of a naught by construction for all n, and fn is a subset of fn plus 1, because if this condition holds true for all n greater than or equal to n capital N, then it also holds true for all n greater than or equal to capital N plus 1. So fn is a subset of fn plus 1, and therefore this implies that fn is a non-decreasing. So this is equivalent to saying that fn is a non-decreasing sequence of measurable sets. So these are all measurable sets, each fn is measurable, this is measurable because fn and f are both measurable functions. So this set is measurable. So fn is a non-decreasing sequence of measurable sets in A0. So these are measurable subsets of A0, and we also have that if x belongs to x, any point, or rather let's take A0, then x belongs to fn for some n, because fn converges to f pointwise almost everywhere. So outside a null set, so for almost every x, in A0, x belongs to some fn for some capital N, due to the pointwise almost everywhere convergence of f these functions fn to the function f. So this means that A0 can be written as the union of all these sets fn, because it's a non-decreasing sequence of subsets, and A0 is a subset of this union. So A0 is actually equal to the union, and therefore by upward monotone convergence theorem, the measure of fn converges to the measure of A0 as n goes to infinity. So since the measure of A0 is supposed to be strictly positive, this implies that the measure of fn is strictly positive for some n in the natural numbers, because this is a sequence of this sequence converges to the value mu A0, and so mu fn is greater than 0. Now the same argument shows that the measure of fn intersection b epsilon is greater than 0 for some n in the natural numbers, because you can simply replace a0 here by b epsilon, and b epsilon we have assumed to have positive measure. So all the arguments that we have mentioned goes through, and this new set fn epsilon has positive measure. Now if we write for x in fn epsilon, so this is fn intersection b epsilon, so this means that modulus of fx minus gx is greater than epsilon. So this is the part, this part follows from the fact that x belongs to b epsilon. And now if I use the triangle inequality here, so you can write this, bound it above by fnx minus fx plus fnx minus gx, and because x belongs to f capital N, then this part is less than or equal to epsilon. So in fact I would like it to have value less than epsilon by 2. So let me go back and change it a little bit. So I would like it here to be less than or equal to epsilon by 2. And so if this is less than or equal to epsilon by 2 and the sum is greater than epsilon, so this means that this is the second term is strictly greater than epsilon by 2. This means that on a set of positive measure, we have fnx minus gx is greater than epsilon by 2 for all n greater than or equal to n. So, this holds for all n greater than or equal to capital N. This is how we defined our set F capital N, which means that Fn cannot converge to G in measure. So, this means that Fn cannot converge to G in measure, which is a contradiction. So, F equal to G mu almost everywhere. So, this finishes the proof of our uniqueness result, comparing limits when you have when the same sequence converges to two different limits in different modes or even the same mode of convergence, then the two functions are equal outside of a null set.